of a diatomic molecule. So the situation is we have two atoms connected by a bond, and these have masses this one M1, this one M2. There is a center of mass. This picture indicates the molecule at its equilibrium position. So this distance is R0. Now, during the vibration, if this atom moves by this much, the other atom must move in the opposite direction because the center of mass should not change. This is definition of vibration. So at this moment, the distance is larger than R0. This is during this stretch. Of course, after stretching, then the motion reverses and contraction starts. So we define a vibrational variable as you see, the vibrational variable is the sum of displacements here. The motion from the equilibrium position to the end of the arrow is called displacement from the equilibrium position. So there is a displacement of this atom and also the other atom. Now, this motion of the two atoms in a concerted manner is equivalent to the motion of a single particle with mass, reduced mass, which is mass 1 times mass 2 divided by the total mass. And the vibrational Hamiltonian is plus where P or P square is minus h bar squared times second derivative with respect to x. So we have one vibrational variable here. This Hamiltonian is in the harmonic approximation. And the explicit Schrödinger equation is minus h bar squared divided by 2 times reduced mass times second derivative plus 1/2 k times x squared times psi equals E psi. This is the explicit Schrödinger equation for the vibrational motion. Please keep in mind that because we have taken the potential energy function up to x squared here, that means we have made the harmonic approximation. The true potential energy function is not exactly a parabola, but we have taken it as a parabola. Now, this is a second order differential equation, as all Schrödinger equations are. There is just one independent variable, it is x, and therefore psi is a function of x. And by solving this equation and making sure that psi obeys the necessary properties of state functions, such as psi should never become infinite at any point at any value for x. It should be continuous. Such conditions are imposed on psi. Then certain results are obtained for psi and the energy. We are not going to discuss how to solve this differential equation, but instead we will take the solutions from literature and just give the final answers. But at least you should be aware of this. This Hamiltonian is the Hamiltonian for vibrational motion, right? Therefore, the energy here in the Schrödinger equation is vibrational energy. Similarly, the psi function is a vibrational wave function. Okay, the allowed values for the vibrational energies as a result of solving this vibrational Schrödinger equation are as follows. Where the vibration quantum number, there is a vibration quantum number. It starts with 0, 1, 2, and so on, all integer, all positive integers. This is the allowed values for the energies here. Now the quantity F0, clearly it has energy unit. It is a fixed quantity. This is the classical vibrational frequency. It is this expression. You see that everything in this quantity is a constant. H is Planck's constant. K is the force constant. and mu is the reduced mass. So these are known quantities when the molecule is specified. For example, if we are talking about hydrogen chloride molecule, then we know the masses, and therefore we compute the reduced mass. What other information do we need? We need the force constant, value for the force constant. That value, we are assuming, is given to us. Or we can just search the literature for what is the force constant for hydrogen chloride molecule. Therefore, this is an energy parameter which is characteristic of which molecule we are investigating. Notice that all the numbers here are positive numbers, and the lowest allowed value is when we put the lowest value for V. What is the lowest value for V? 0. So the lowest possible vibrational energy is 1/2 F0. What do we expect for the lowest vibration energy classically? 0, relative to the same reference point. We see that this number is not 0. Therefore, what was our definition of 0-point energy? Lowest quantum mechanical value minus lowest classical value. Lowest classical value is almost always 0. So we just look up the lowest quantum energy to see if it is 0 or not. Here we see that it is not 0. Therefore, this is a 0-point energy. But we should attach another word to this 0-point energy, because there are several types of 0-point energy. For example, in the discussion of linear motion, we mentioned translational 0-point energy. So here we will call this vibrational 0-point energy. 0-point energy, but we added a vibrational part to see which motion this corresponds to. Now, let us remember the true potential. This is the true potential. This is equilibrium. It corresponds to the minimum in this. Now, the harmonic potential is a parabola which is fit to this curve. This is 1/2 kx square. Harmonic potential. This is the true potential. Now, our result for the allowed energies that result is obtained by taking the parabola for the vibrational potential energy function. But you should notice that in the lower part of this figure, the parabola fits very nicely with the true potential. Therefore, the results we obtain from the parabola approximation, the harmonic approximation, should not differ very much from the true vibration energies if we had used the exact potential energy function here. So, now, this is molecule AB, this is A plus B, dissociated. Now, this difference we had defined as dE. It's kind of dissociation energy, but I had warned you that this is not the experimental dissociation energy. Why? Because definition of dissociation energy is this. Total energy of the products, A plus B, minus total energy, the lowest possible energy of the molecule. The lowest possible energy of the molecule AB is not zero here. Why? Because as you see here, there is a 0 point energy, vibration 0 point energy. So if we indicate it on this graph, the lowest energy, this is 1/2 F0. In other words, vibration 0 point energy. This is the lowest possible value for the vibration energy. So, the true dissociation energy is, as I have just defined it, total energy of the products, A plus B, the dissociated atoms, minus the lowest energy for the molecule. The lowest energy for the molecule is this value. So, this energy difference is the true or experimental dissociation energy. Therefore, you see the relationship between these. If we know the electronic dissociation energy and the 0 point vibration energy, then we can calculate the experimental dissociation energy, as you see from the figure. So this is then experimental dissociation energy. This is the electronic dissociation energy, and as you see here, from the minimum of the potential energy curve to the dissociation limit. And clearly, experimental dissociation energy is a number which is smaller than the what we called dissociation, electronic dissociation energy. Okay, so keep this in mind, that the observed dissociation energy is related, it is this one, related to the electronic dissociation energy and the 0 point vibration energy in this manner. Now, this full curve, the exact curve, theoretically is obtained by solving the Schrödinger equation for the electrons. All right? So it's something theoretically obtained. And this curve is obtained. And then that also means that calculation produces the numerical value for the electronic dissociation energy. But when we compare our results with experimental values, we have to make sure that we are doing it correctly. And from the discussion, it should be clear that the lowest energy is this. The lowest vibration energy is this value. It is not zero. If the lowest energy were zero, then this quantity, electronic dissociation energy, would be the same as experimental. However, the lowest vibration energy is not zero. There is a 0 point vibration energy, vibration 0 point energy, and as a result, we have such a relationship. Now, let us show these allowed energies using an energy level diagram. I'm just showing these values using a diagram, energy level diagram. The next level is this is V equals 0, this is V equals 1, this is V equals 2, and so on. So, we see that vibrational spacing from one level to the next one, the adjacent. What is the difference between this value and that value? 1.5 minus 0.5, 1. The difference between that value, 2.5 minus 1.5, 1. So vibrational levels are equidistant. This is something which we see immediately. Okay, equidistant vibrational levels. And the difference between the two levels is just F0 and so on. We are going to discuss the populations of the vibrational energy levels. Now, our Boltzmann expression requires also degeneracy information. Now, this problem, the vibration problem, has just one variable. It is the x variable. Whenever the problem contains only a single variable, there can be no degeneracy. That means every vibration level is non-degenerate. In other words, for each of these allowed energies, there is only one vibrational state function, not more than one, which means the G factor is 1 for all vibration levels. Are non-degenerate. Now, just using this information, let us consider an example. Let us take in fact, chlorine 35 isotope of HCl gas at, again, 300 Kelvin. Previously, we have considered such a sample and examined the populations of the rotational energy levels at 300 Kelvin. This time, we are asking what are the populations of the vibrational levels. These are all the allowed vibrational energy levels here. So we have a sample, macroscopic sample. We are asking how many of these molecules in the sample are in the lowest vibrational level? How many others are in the first vibrational level, and so on, the distribution. The answer to such questions is given by the Boltzmann distribution expression. So Boltzmann distribution expression is an important expression because it allows us to give answers to such questions. Let us remember the Boltzmann distribution. Relative distribution. By definition, one means, in this expression, one means the lowest energy level. So here, in that expression, one means this level. 1, 2, 3, 4, and so on. It's continuing. So when you change the notation indices, just make sure that notations don't get confused. Here, G factors are degeneracies of the jth level. Now, previously, I have applied this same expression to the rotational distribution by using the rotation energies here. Now, I will do the same thing, but this time I'm going to use a vibrational information, okay? And vibration energies, allowed vibration energies are these. So now I can write this. I'm now changing my notation. This is my general expression, but now I'm using the V quantum numbers. So NV, the number of molecules at the Vth vibrational energy level, divided by number of molecules in the lowest level. So this is a relative population. Population of the Vth vibrational level relative to those in the ground vibrational level. All vibrational levels are non-degenerate, which means all G values are 1. So this factor is 1. Then e to the minus EV minus, what is the V value for the ground level, lowest energy level? 0, isn't it? EV minus E0, as you see here, V times F0. So this expression takes the following, e to the minus V times F0 over KT for V equals 0, 1, 2, and so on. Of course, by definition of relative population, for V equals 0, this has value 1. Relative population, lowest level, relative to itself, is of course 1. What is important is, what are these numbers for? V equals 1, V equals 2, the excited vibration levels. Are there significant amount of molecules at those energy levels? That's our question. Remember, in the case of rotational levels, there was a large distribution. Now, to do this calculation, we need data for this value is given 2009.95. This is given in wave number units. I want to calculate F0. By definition, F0 is H times the frequency. But this expression is assuming SI units. All right? So in order to use this expression, you must express the frequency in which unit? What is the unit in SI? SI unit for frequency, hertz. But the data is given in wave number. So you should remember the conversion factors. What was the conversion factors from wave number for frequency to hertz? Frequency in 1/2 is C times frequency in wave number unit. Remember? So if you want to use this expression to calculate F0, and if the frequency is given in wave number unit, you must multiply this number with speed of light in centimeter per second, remember. All right? Then the result is going to give you the frequency in hertz unit. Then you multiply with H, you will obtain the energy. But because you are using SI units, the unit for energy will be joule. All right? Okay. So if you take this number, multiply with speed of light, then with H, you will get F0. That F0 you may use here. In that case, because you have used SI units for F0, you just take the value of Boltzmann constant and T, multiply it. It will also be in SI units. Then do the division and then continue. But instead of doing this, you may remember that E in joule is given by H times C times E in wave number unit. In other words, this wave number unit can be regarded either as frequency unit or energy unit. If you are regarding it as frequency unit, the conversion factor is C. If you are regarding it in wave number as energy unit, the conversion factor is H times C. In other words, this number here, which is given as frequency data, but the numerical value in wave number unit can be regarded directly the value of this energy, but in what unit? Wave number unit. Okay. So F0 in wave number unit is just this do you understand what we are doing? Look, how do you convert this number to SI unit? Take this value, multiply with C, then with H. What will happen? This side, H times C times isn't it? But this is equal to H times C times E in wave number unit. So what do you see? HC will cancel, and the energy in wave number unit will be directly this number. Okay? In other words, it is not necessary to do any calculations for changing conversions, for changing units into SI units, for example. But you have to get used to using wave number unit either as frequency unit or energy unit. Now, if I use wave number unit for this, so directly I take the frequency value, vibration frequency value, and I say this is my F0, but in wave number unit. Then, in a calculation of this type, units must be consistent. If I take this value in wave number unit, I have to convert KT into same unit. So what I do is, use the tabulated value for K, Boltzmann constant. These constants are always given in SI units. Multiply with T. T is 300 Kelvin. The unit will be in joule. To change it into wave number unit, same unit as this one, what was the conversion factor? You see it over there. HC, isn't it? So multiply this and then divide by H times C. Okay? This will give in wave number unit. If you do this, you will obtain 208.6 for the thermal energy, KT, in wave number unit. Now, this quantity, F0 over KT, this is for T300. This 29995 divided by 208.6. Energy units are same, wave number units. You do the division, and this is 14.34. So what happens? If we write V here and relative population, this is 1 by definition. You put V equals 0, this is e to the 0. Now, for V equals 1, the next level, it is e to the minus 14.34. Or this is 5.9 times 10 to the minus 7. What do you see here? If we assume the population of the lowest level is 1, relative to that, population of V equals 1 level is 6 times 10 to the minus 7. All right? It's a very, very small number relative to the lowest level. If we go further, then it's, you put V equals 2 here. It means square of this number. So, as the vibration energy gets higher, numbers become drastically smaller and smaller. So, what do we conclude from this discussion using the actual numbers? Look at here. The number of molecules in higher vibration energy levels is extremely smaller than those molecules in the ground vibration level. Because the relative populations, look at 10 to the minus 7 relative to 1. This is 10 to the minus 14, and as vibrational energy goes up, numbers become much, much, much smaller. So, the net conclusion here is that our macroscopic sample, of course, contains Avogadro's number of molecules. Effectively, all of these molecules are at 300 Kelvin. All the molecules are in the ground vibration level. All right? All molecules at V equals 0 vibrational level. Such information is needed to interpret experimental results because the data about the sample, to get the data, the usual method is to use light. Shine light and look at absorption as a function of frequency of the light and interpret. Now, for the interpretation, we have to know the initial states of the molecules. So in this case, the initial vibrational states of the molecules in the sample. This argument is telling us that it is, we may assume all the molecules in the sample to be in the lowest vibrational level. And if there is any absorption, only those molecules will absorb. All right, let us give a break now.